So I will be talking about, in principle, what we've been doing within Spearhead, but also the ESA project for Mod 2 that we had. And that's building a catalog of Forbush decreases across heliosphere and the Forbush decrease analysis tool. So first, just an introduction, but already Alexis mentioned that. So for CMEs, we kind of see them as two structure things. So they have a magnetic structure, which is presumably a flux rope or twisted magnetic field structure. So a structure in which magnetic field lines are helicoidally winding around some central axis, and as they move through interplanetary space, they push and drape the interplanetary magnetic field, forming so-called sheath region in front, which is compressed, turbulent. And these, of course, reflect on the in situ measurements that we observe. So in principle, in a typical CME, we first observe this compressed and turbulent sheath region, followed by a smoothly rotating magnetic field, which shows also the expansion profile in flow speed, low temperature, and low beta. And correspondingly, we also observe the depression in the galactic cosmic rays. In a typical example, we see a so-called two-step Forbush decrease, the first step coming from the shock sheath region, and then the second step, which is more symmetric, corresponding to the borders of the flux rope, magnetic cloud, the magnetic obstacle, or however you want to call it. And in our study, we are only interested actually in this part, so the one which corresponds to the flux rope. Yeah, this is just a show how a flux rope looks locally. So we assume it's kind of a cylindrical structure with a rotating magnetic field. So there are some open questions about Forbush decreases. How are they formed, and how do they reflect CME properties? It's actually related questions. And these actually relate to the transport, to the particle transport. So they directly, these open questions directly relate to Spearhead science question 3, which is what are the key processes of high energy particle transport in the interplanetary medium? And one way how we can try to answer those questions is using modeling. And a couple of years ago, we developed this Forbush decrease model. This is not a new idea. It's built on, well, basically almost a century of research. It kind of reduces the transport equation, the Parker's transport equation, to a diffusion equation, which is based on perpendicular diffusion of particles in the flux rope. I listed here all the people who contributed to the idea. Our contribution to this idea was that we assume a self-similar expansion of arbitrary type. So in principle, this self-similar expansion is given by the drop in the magnetic field and the increase in the size of the flux rope, and we assume that this can be given by any type of power law. Of course, it needs to be within the constraints that we have from observational studies. And this model, once you solve the equation, the good thing is that you can solve the equation analytically, gives a solution which has a time-dependent and a space-dependent part. The space-dependent part is, in principle, the Bessel function. So it assumes that the profile of the Forbush decrease, which corresponds to flux rope, will always be symmetric and will be given by the Bessel function of the 0th order. And the only thing which will change is the amplitude. And the amplitude is something that changes with time. It depends on the diffusion coefficient, which means initial magnetic field. It depends on the initial radius of the flux rope and also how it expands. So it directly depends on the expansion factors for the magnetic field and for the size. And in this project, in principle, what we want to do is we want to build a list of Forbush decreases. We want to analyze observationally Forbush decreases, but also as part of work package 7, we want to apply this Forbush decrease model for mode to the observations that we have. These are some examples of Forbush decreases near Earth. Here, Forbush decreases were measured by SOHO-EFIN. So each of these plots shows a couple of panels which correspond to magnetic fields. So the first two are magnetic field. The top one is total magnetic field fluctuations. Then we have the three components of the magnetic field. Density in black, temperature in red, and the so-called expected temperature in blue. It's a kind of empirical formula where this expected temperature depends on speed, and wherever the temperature is lower than the expected temperature, in principle, we expect to see a CME. And this panel shows the speed and the plasma beta. CMEs are of course, low plasma beta structures, and the lowest panel shows measurements from SOHO-EFIN detector F, which was found suitable to observe Forbush decreases. However, it should be mentioned that we typically observe Forbush decreases in weaker CMEs because the stronger ones, which are very fast, they draft shocks, and then the low energy particles which are bouncing around the shock, they totally eat up the Forbush decrease, so we cannot observe it. And from these examples, which are shown here, you can see that we can expect quite some variability. So, for instance, this one is nice and symmetrical. This one is not really symmetrical. This shows some substructuring, and this one never returns to pre-increased levels. So even when we look at, let's say, nicer ICME examples, we can expect basically anything. So when we were performing our measurements, we had to tackle with the border selection problem. So you will notice that there is quite some freedom where you will set the borders, and this is especially important if you want to apply modeling on your data. So we decided we will actually take several border selections. So we apply something that we call the inner nice structure. So it would typically be some nice Forbush decrease, probably only one substructure, which corresponds to nice ICME parameters like low temperature, low beta, nice rotation, or whatever. But we also noticed that in many events, we can apply something that we call extended borders. So this is something that might encompass also outer parts of what was initially flux rope. It often takes parts of sheet or something at the back of the ICME, but we also find that we can fit it with the model. And then we introduced a totally subjective border. This is an optimal border. So this is a subjective view of the observer who will fit the fit. So this is something that the observer says, I can best fit here. We don't know to what it corresponds. It should be mentioned that we did this particular border selection because we did it for the ESA project, and then we simply adopted the same procedure here in Spearhead. And then we also allow the observer to make some kind of visual characterization. So this was based on a study where we were looking at SOHO-EFIN Forbush decreases. We noticed that when you try to fit this form mode, you can have different, let's say, classes of fit. So you can have something which is a good fit, then you can have something which is symmetric, but the data is asymmetric. So we would call this asymmetric fit. You can have a fit which only has couple of data points, so not very reliable. You can have a fit which has huge data scatter, so again, not very reliable. You can have a fit where the data never return to pre-decrease level, whereas the fit does. And you can have also substructures within the fit, but when you fit, you make a single fit, but you see that in the data there are actually a couple of substructures. So this was our measurement method, and here I will just shortly demonstrate how our measurement tool looks like. So this is the Forbush decrease analysis tool. It's a GUI. When you open it, you get this window. You put the observer's name or designation, whatever. This will appear in a string, which is ID of each measurement. You put in the data, where you want to plot the visualization window, where you want to perform the measurement. And there are actually at the moment several analysis tools. So in Spearhead, we only use this 4-mode analysis tool, but we now also have in situ analysis tool, sheet analysis tool, and Lundquist Fit, which we actually use for other projects that we have. And I will just show you an example at Solar Orbiter. So here you choose which spacecraft you want to observe, and then you start the analysis. This opens this window which visualizes magnetic field, plasma, and galactic cosmic rays, and then you kind of mark the borders where you want to make the measurements and perform the fit. So we do both at the same time. This upstream region which you have to choose is something that we used in the ESA project. It's not important for Spearhead. Here you can decide whether you want to take inner, extended, or optimal borders. And then when you press calculate, this will open a window where the fit is shown. And then if you are happy with the fit, you just make some descriptions of the fit. You can add some notes, and then you save the event. And when you save it, okay. And then if you go to the output, you find your spacecraft, 4-mode analysis, and there is for each event that you analyze, there will be a folder which shows a figure and the results, and also all the results of all the events are saved in a CSV file. And this CSV file will then be, once we have all the measurements ready, they will be uploaded to Spearhead Nextcloud. And you can see here that there are a bunch of measurements which are performed. So within the borders that you selected, in principle, what the code will automatically calculate is average, peak, median, and standard deviation of speed and magnetic field, the amplitude of Forbush decrease, and of course it will also make a note of at which position the detector was, which latitude, longitude, and so on. And getting back to the presentation. Okay. So here are some typical examples of the measurements that we performed. So this is an example at Helios 1. So one thing that you can notice here is that the magnetic field is something like 120 nanotesla, so huge. This is, of course, because it's at 0.3 AU. Also, this is one example with Solar Orbiter at 0.5 AU, where you also see a nice Forbush decrease. Then we have 2 examples from Earth, one with South Pole neutron monitor and one with SOHO-EFIN. This is the same event. The magnetic field is slightly different because for South Pole we used Omni, which is given in GSE coordinates, and for SOHO-EFIN we are using wind, which is in RTN coordinates, but it's the same event. One thing to notice is that the Forbush decrease detected by South Pole neutron monitor and SOHO-EFIN is quite different. And this is, of course, because they are looking at different energies. And some examples that I actually showed yesterday. So at Mars with MSL RAD, we typically observe only the shock sheet part of the Forbush decrease, not really the flux rope part. And at Ulysses, we can observe this flux rope part, but it's very noisy. And this is the current status. So part of the measurements were done in the scope of this ESA project for Mode 2, and part of it was done with Spearhead. We cross-checked all the events that we measured with the existing lists. I will not mention them now because there are many. And currently we have something, not currently, by the time we will finish, so this is what we currently have, but by the time that we finish, we expect to have something like 1,000 events measured through 100 years of time series observations in a time period of 50 years. So this will be a huge list of Forbush decreases in the heliosphere. So this means we will have a lot of work performing the statistics, which will be done in the upcoming period. But I think that will be the most interesting part of this study. So unfortunately, I don't have any preliminary statistics results to do, because we are still wrapping up measurements of Ulysses, Mars, and neutron monitors. So that's it.